anyone who wasn't here can see this here. So section 11.1 sequences. So the first thing here is the definition of a sequence. So a sequence is a function whose domain is the set of, I'm going to focus this a little bit more, but I'm in the basement because it's actually the best place for me to be, oddly enough. So it's the function whose domain is a set of positive integers, and the individual numbers that appear in a sequence are called the terms of the sequence, and a sequence having only a finite number of terms is called a finite sequence. And otherwise, a sequence is considered to be an infinite sequence. So the general term, or the nth term, is denoted by a sub n. So here's an example. A sub n equals 2 to the n is a sequence. So then if I substitute the domain, which is the set of positive integers, so n is equal to 1, 2, 3, all right, and so on. So then a1 would be 2 to the 1, a2 is 2 to the 2, a3 is 2 to the 3, a4 is a4, and I wrote the 4 in the wrong spot here. So a4 is 2 to the 4, etc. These are the terms of the sequence. All right, so these are the terms of the sequence. So now, actually, I want to make sure that you can read this here. So sequence, all right. So now, how do you tell whether a sequence converges or not? So you write that the limit as n goes to infinity of a sub n is equal to L, and say that the sequence a n converges to the limit L, provided that for each positive number epsilon, there exists a positive integer n. So that could possibly depend on epsilon, such that the difference in absolute value between a, n, and L is less than epsilon, wherever the lowercase n, this n, is greater than or equal to this positive integer that we said existed. And a sequence that converges to a limit is called a convergent sequence. Otherwise, it is said to be divergent. So determine whether the sequence a n is, let's see, 1 plus 1 over n to the n power converges or diverges, and if it converges, find its limit. So let's see. So let's just start with n, and 1 plus 1 over n to the n. So if n is 1, I get 1 plus 1 over 2 to the 1 power. So that, sorry, 1 over 1. So now 1 plus 1 over 1 is actually, well, that's 2. So 2 to the 1 is 2. Then if n is 2, 1 plus 1 over 2 to the 2 power. So that will end up being, let's see, so that's 3 halves to the second power, or 9/4. So that's 2.25. And then I could keep on going, like 3, that's 2.3704, 4, 2.4414. So it's definitely going up fairly slowly. So 5, 2.4883. So I want to know if this actually gets to some limit or not. So I'm going to jump up to say a thousand. All right, so at 1,000 I get 2.716923932. All right, and then if I jump up even higher, let's say a million, if I substitute in a million for n, I would get 2.718280469. And let's try, let's try a billion. So 10000000000. So I get 2.718281827. So you see that this is closing in on some number, right? And that number happens to be E. So in other words, we can write that the limit as n goes to infinity of a sub n is the limit as n goes to infinity of 1 plus 1 over n to the n power is actually e to the first power. So therefore, this converges to e. So on a side note, if you were interested in knowing, then so here's a side note for you. The limit as n goes to infinity of 1 plus k over n to the n power will be e to the k power rather than e to the first power. So actually, this is the. I'll slide that back up in a moment. But this is the number that actually determines what the exponent, the e, will be here. So just keep that in mind there. So now let me talk about the properties of these limits of sequences. All right, so how are you doing, Maxwell? Can I move this off the screen? Okay, good. So the properties of limits of sequences. So let the function f be defined on the interval from 1 to infinity. So this is a bracket here on the 1. And I'm going to focus this. I don't know what is going on with this lighting here. But so in define the sequence a sub n by a n is f of n for each positive integer n, then if the limit as x goes to infinity of f of x equals L, then it follows that the limit as n goes to infinity of a sub n is equal to L. So here's an example. Suppose that a sub n equals f of n for each positive integer n, and that the limit as, this should actually be x goes to infinity, not n, of x goes to infinity. Oh, yeah, so if that should be, yeah, so I'm going to erase this. This should actually be this statement here. Limit as x goes to infinity of f of x equals L. Then prove that the sequence a n converges to L. So here's how we're going to do that. By definition, if you recall, then the epsilon is greater than 0. So then there exists, so this is the symbol for there exists a k greater than 0 such that the absolute value of f of x minus L is less than epsilon for all, so that's for all x greater than or equal to k. So now let's suppose that capital N is an integer, integer such that the capital N is greater than K, then in particular, you would know then the absolute value of f of n minus L is less than epsilon. So that was by our where was it? Our supposition here, all right, and that's for all n greater than capital N. So what does that mean? This means that the limit as n goes to infinity of a sub n is equal to L, and therefore, so that's the therefore, the sequence an converges to L. So really, this is just a proof of what's going on here. So just remember that if this wasn't something that was true, then most of the stuff that we did here we wouldn't be able to do. So let's give the properties here, and then we'll do a few examples. So suppose that the sequence A, N, and Bn converge, and that C is a constant, then the following properties hold. The limit as n goes to infinity of C is equal to C, and the limit as n goes to infinity of C an is C times the limit as n goes to infinity of an. So what I'm saying is that most of these properties of limits that you know of for functions are going to hold for sequences as well here. So limit as n goes to infinity of an plus or minus bn is equal to the limit as n goes to infinity of an plus or minus limit as n goes to infinity of bn. And then we have the limit as n goes to infinity of an times bn. So that would be the limit as n goes to infinity of an times the limit as n goes to infinity of bn. All right, so let me go ahead and get the next page here. And I have to turn the lights back on because my lights are on a timer that turns them off every 60 minutes. All right, so so now let's go to property 5 here. So here's property 5. If Bn is not equal to 0 for all positive integers of n, and the limit as n goes to infinity of Bn is not equal to 0, whoops, then the limit as n goes to infinity of an over bn is the limit as n goes to infinity of an over the limit as n goes to infinity of bn. All right, so I'm going to move this up, but before I go on, are there any questions, Maxwell? Yeah. So as I mentioned, like I think that you'll see that these are the same properties of limits for functions essentially, and we're just applying them to sequences now. So these shouldn't be as difficult as they might seem. So here's another one. If k is a positive constant, then the limit as n goes to infinity of c over n to the k is equal to 0. And then here's number 7. If the absolute value of c is less than 1, then the limit as n approaches infinity of c to the n is equal to 0. And then finally, if the absolute value of c is greater than 1, then the sequence C to the N actually diverges. So you just want to make sure that you're clear on those two items right there. So here's some simple ones here. Determine whether each sequence converges or diverges, and if it converges, find the value L. All right, so consider this here. 3 plus negative 1 to the n power. So the an is 3 plus negative 1 to the n power. So what I want to do then is find the limit as n goes to infinity of an. So that would be, where is it? Oh, limit as n goes to infinity of 3 plus negative 1 to the n. All right, so what I'm actually going to do is just list out some terms here. So n and 3 plus negative 1 to the n. So we have n is 1, 3 plus negative 1 to the 1, that it would be 2. 2, 3 plus negative 1 to the 2, that would be 4. 3, 3 plus negative 1 to the 3, that's 2. 4, 3 plus negative 1 to the 4, that would be 4. And 5, you get a 2. 6, you would get a 4. So hopefully you can see the pattern is 2, 4, 2, 4, 2, 4. So that means this limit does not exist because the terms keep on alternating between 2 and 4 and don't go to any particular value here. So in other words, so since the terms of the an, 3 plus negative 1 to the n power, alternate between the 2 and the 4, that means therefore the sequence 3 plus negative 1 to the n diverges. All right, so I don't want to see them alternate. I want them to converge to the like a finite limit L there. All right, so we'll also see other ways in a little while, other ways that these sequences might diverge. But if you've noticed, though, in a couple of cases here, like in this example and the one that had the E in it, I did list out the terms to help me figure out if this is converging or diverging or give me some sort of idea of what the sequence is doing. So if you get stuck, sometimes listing out the terms is a good way to go about doing this. But the same instructions here. Determine whether each sequence converges or diverges, and if it converges, find the value of L. So this is an here. So we want to find the limit. Here, I'll pull that up here so that will make it easier for you. But if you ever have a question or want me to go back, just let me know. But the limit as n goes to infinity of n over 1 minus 2n. So for limits as n goes to infinity, I actually can go ahead and divide each power of the numerator and denominator by n. So this will be the limit as n goes to infinity of, well, n over the limit as n goes to infinity of 1 minus 2n, and then I'll divide every term by n. This is a technique that hopefully you have seen before because n over n is 1 and 2n over n is 2. So I'm left with the limit as n goes to infinity of 1 over limit as n goes to infinity of 1 over n minus 2, but the limit as n goes to infinity of 1 over n is 0. So this term right here goes to 0. So I have 1 over 0 minus 2. That's negative a half. So that means, therefore, the sequence n over 1 minus 2n converges to the negative a half. You could make a table for this as well, but this one really, it wasn't necessary to do that here. All right, so now let's consider the sequence of n squared over 2n minus 1. So we want to find the limit as n goes to infinity of n squared over 2n minus 1. So generally, if I want to do this, I, I, I want to make sure that I follow this rule here that we're actually talking about the sequences here. All right, so I did show you a lot of properties for these limits of sequences, but I didn't actually show you anything that was like L'Hopital's rule or anything like that, which is probably the easiest way to go about that. So let me just, on the side here, consider the function f of x equals x squared over 2 to the x minus 1. Then we have the limit as x goes to infinity of x squared over 2 to the x minus 1. And this is of the form infinity over infinity. So that means we can use the L'Hopital's rule to find the limit. So the derivative of the x squared is 2x, and the derivative of the 2 to the x minus 1 is 2 to the x natural log of 2 minus the derivative of 1, which is 0. But I still have an indeterminate form of infinity over infinity. So I need to use L'Hopital's rule again. So use the L'Hopital's rule again. So now I have limit as x approaches infinity, derivative of 2x is 2, then derivative of 2 to the x natural log of 2 is 2 to the x natural log of 2 natural log of 2. Now, what I can see is that this part right here is all a constant that I can bring in front of the limit here. So I have limit as x approaches infinity. So I'll bring that in front. So I have 2 over natural log of 2 squared, all right, out in front here. So that would be 1 over 2 to the x still. And then what I actually can do is write this as 2 over natural log of 2 squared. And then I have limit as x approaches infinity of, now what I'll actually do is rewrite this as 1/2 to the power of x. And then what I'll notice here is, if you recall, some constant to the power, all right, is either 0 or diverges depending on what c is. So since the absolute value of 1/2, so c is equal to 1/2, is actually less than 1, that means that this limit is equal to 0, all right, by this part right here. All right, so if this absolute value of that base c is less than 1, then the limit is 0. So then that means we have 2 over natural log of 2 squared times 0, which is 0. So therefore, this is also 0. So therefore, the sequence n squared over 2 to the n minus 1 converges to 0. So that was a little bit of a different example that demonstrated that rule of the c to a power there. But now I want to do the same thing now, but instead of giving the nth term formula for the sequence, we're given just the list of terms of the sequence. So before we do that, do you have any questions, Maxwell? Yeah, so the so you take it says that if you have an indeterminate form like infinity over infinity, then this limit, the limit of say x approaches infinity of say like this f of x over g of x, then would be equal to limit as x approaches infinity of f prime of x over g prime of x. That's what I did. Yep. All right. So now for the sequence 2 4/3, 8/5, 16/7, 32/9, we need to figure out what the nth term is first. So the numerator, like if I look at the numerator, I know that I have, and by the way, I know that I have a1, a2, a3, a4, right, a5, and eventually I want to get to the nth term, but I know that the numerators are all 2, 4, 8, 16, 32, but I could write this as 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power. So this would be 2 to the nth power in the numerator. Then I see the pattern of just the odd numbers 1, 3, 5, 7, 9 in the denominator. But that would be, that would be 2 times 1 minus 1, 2 times 2 minus 1, 2 times 3 minus 1, 2 times 4 minus 1, 2 times 5 minus 1. So the nth term is 2n minus 1. So here is the nth term. So now I'm going to do the same thing as sort of before. I am going to consider the f of x, which is 2 to the x over 2x minus 1, and find the limit as x goes to infinity of 2 to the x over 2x minus 1. And I see this is an infinity over infinity form, so I can use L'Hopital's rule again. So the derivative with respect to x of the numerator, the 2 to the x, is 2 to the x natural log of 2, and the derivative of the denominator is 2, so that's the derivative of the 2x minus 1. And then I see that there's a a constant that can be brought in front of the limit again. So I have natural log of 2 over 2 times the limit as x goes to infinity of 2 to the x. But in this case, I see that if I have c is equal to 2, the absolute value of 2 is actually greater than 1. So therefore, that means that this sequence will diverge. So the sequence of 2 to the n over 2n minus 1 actually diverges. So that one was very similar to the one before, but we had to figure out what the nth term was our self there. So the same thing for this next example here. Consider the sequence of -2, then 4, -13 over 3, 10 over 3, and -121 over 60. So A1 is -2, A2 is 4. And remember, I want to try to find some pattern here. So A3, -13 over 3, A4, 10 over 3, A5, -121 over 60, and I want to get to an nth term. Well, if I told you that this would be a I'm going to rewrite these so that you can see a little bit better, but -2 over 1 is still -2. 8 over 2 will still be 4. -26 over 6 is still -13 over 3. 80 over 24 is still 10 over 3. And -242 over 120 is still -121 over 60. But then I can see right away what's actually happening maybe in the numerator. I see that every other term happens to be negative. So I have negative, 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 and then the whatever the term is. And in the numerator, if I look at this, well, I could rewrite the 2 as 3 minus 1, the 8 as 9 minus 1, the 26 is 27 minus 1, the 80 is 81 minus 1, and the 242 is 243 minus 1. So then, well, that should be sort of maybe a little bit obvious now why I happen to look for these, because these are actually the powers of 3. So 3 to the 1 minus 1, and then 3 to the 2 minus 1, 3 to the 3 minus 1, 3 to the 4 minus 1, and 3 to 5 minus 1. So that's similar to how I looked for the powers of 2 in the last example. I tried looking for powers of 3 in this example. So if I want to start by alternating the negatives, I have -1 to the nth power will make every other term negative, starting with the first one. Then I have 3 to the n minus 1, and now I just have to deal with the denominator. But the pattern of 1, 2, 6, 24, 120, if you don't recognize that, I have 1, and then 2 times 1 is 2, then 3 times 2 times 1 is 6, then 4 times 3 times 2 times 1 is 24, and then 5 times 4 times 3 times 2 times 1 is 120, and those are the factorial. So 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. So here we have n factorial. And then if I look at the limit, then the limit as n goes to infinity of an, this -1 to the n, 3 to the n minus 1 over n factorial, then what will this equal? Well, there's a lot of ways that you can visualize this here, but let me just try to pull up my calculator so that you can at least see what I mean here. So if I treat it like a function of x here, so I have -1 to the, say, x power. All right, so with the x power times the, where's the oh boy. Oh boy. Okay, I just want to put in the fraction here, but there. 3 to the x power minus 1. See, my calculator has been doing weird things all week, and actually, I was trying to figure out all week why my calculator has been drawing a weird line on my graph, and seeing why 0 all the way down here was log 3. Like, I don't know why log 3 was there, but I'm going to get rid of that, so hopefully the weird line will not be on my calculator when we graph this here in a second. But now I have to get rid of this parenthesis here, but I actually don't know why it did this. I don't know. And then we need x factorial in the denominator, so x factorial, and then we'll graph this. And, well, all right, so let's try to substitute some really large numbers, like 100. So if even 100 is too big for this, so let's try 10. So 10 you get 0.016. So let's try 20. Do you see already at 20 you get a number that's actually really close to 0. So at x was 10, we get 0.016272045 and at x was 20, we had 0.00000001433179137. So I think that I'm safe to say that this is going to be 0. So therefore, the sequence AN converges to 0. So, do you have any questions about that one, Maxwell? Oh, yeah, yeah. Math and then PRB, yeah. Yeah, so I thought that was kind of interesting to see that even the calculator couldn't really even put in 100 because it already was so small that it went beyond the number of digits the calculator could even store. So so it means it got to be a limit of 0 fairly quickly, but that's because as the factorial increases, these denominators get really large quickly as well. So here is the increasing and decreasing sequences. So a sequence AN is said to be increasing if the AN is less than or equal to AN plus 1 holds for all positive integers n. And similarly, a sequence is decreasing if AN is greater than or equal to A sub n plus 1, and a sequence that is either increasing, and that could be, or decreasing, is called monotonic, and otherwise it is called non-monotonic. So determine whether the sequence 3 plus -1 to the n is monotonic. And we had this one, I think that we had this one at the very beginning, if you recall, because it was the one that alternated, right? So we did have that one. All right, so the the terms were 2 4 2 4 2 4. So since they well, AN was 2 4 2, 4, 2, 4. All right, so since AN alternates between the 2 and the 4, it is non-monotonic. So we can see that it was neither increasing or decreasing. It just kind of alternated 2, 4, 2, 4, 2, 4. Now, let's consider 2 to the n over 1 plus n. So the first thing that we really need to figure out then is the an greater than or equal to an plus 1, or is an less than or equal to an plus 1. So that will tell us whether this is going to be actually like decreasing or whether this is going to be an increasing sequence. All right, now one actual way that you might want to actually go ahead and do this is just start by listing out some terms to see if you have a hypothesis of whether this might be increasing or decreasing. So if n is say 1 and you have an is 2n over 1 plus n, and n is 1, we have 2 times 1 over 1 plus 1, that is a 2 over 2, 1. If n is 2, I have 4 over 3. N is 3, I get 3 over 2. And if n is 4, I have 8 over 5. Now, the only thing that you want to be careful of is if for some reason, like one of these, like if for some reason the sequence ends up at some point starting to turn around and go from increasing to decreasing, then it would not be monotonic. So at this point, I can hypothesize that this seems to be increasing because it seems to be 1, 4 over 3, 3 over 2, 8 over 5, and it seems to be going up. But is it for sure? I'm going to check. Is 2 to the n over 1 plus n always going to be less than or equal to 2 times the n plus 1 over 1 plus n plus 1. So when I substitute the n plus 1 in for n, is this always going to be greater than or equal to this, or is this always going to be less than or equal to that? Well, all right, if I distribute the 2 here, I have 2n over 1 plus n less than or equal to 2n plus 2 over, this will be, if I combine like terms, n plus 2. Now, since the n is actually a positive integer, right, greater than or equal to 0, so actually 1 even. All right, so n is equal to 1, 2, 3. I don't actually have to worry about if I have anything strange going on with the inequality. So don't worry about that quite yet. But what I really want to do is, like, if n is going to infinity, if at the nth term, right, for any term, I can determine whether this statement here is true, then I know that this is always going to increase and that it's monotonic. So let's just take the limit as n goes to infinity of 2n over 1 plus n less than or equal to the limit as n goes to infinity of 2n plus 2 over n plus 2. And I know then that because this is an infinity over infinity and infinity over infinity, I can use L'Hopital's rule. So limit as n goes to infinity of 2 over 1 less than or equal to limit as n goes to infinity of, so again, L'Hopital's rule. So that's less than or equal to the limit as n goes to infinity of 2 over 1. So I get 2 is less than or equal to 2, which is true. So therefore, yes, the an is monotonic. monotonically increasing. All right, so there you go. This is monotonically increasing. So now let's actually go ahead and consider this next one. So do you have any questions about that one, Maxwell? All right, yeah, so that one, as I said, just make sure that the terms are always going to be increasing by proving it, because if you look at the next one, and I have the n, and then I have the an, if I have 1, I have 1, 2, that would be, well, 2 squared over 2 to the 2 minus 1, that's actually 4/3. Then 3, I get 9/7. 4, 16/15. 5, I get 25 over 31. And 6, I get 36 over 63. So if I look at the terms here, and they were 1 4/3, 9/7, 16/15, 25 31st, and 36 63rds. You can see that at some point the the value was greater than 1, but then the next term it turned back around and it went to less than 1. Right, so the values were going up, and then they made a turn and went back down. So in this case, I would say, therefore, AN is non-monotonic. So this is why I said that even if you actually list out the first few terms and you think that it's increasing, that you should still prove it, because there might be a case when it's like this and the terms would turn back around, and that would be really bad. All right, so sometimes, like, one of the best things to do is exactly that. Just list out the terms and see what happens there. So now let's talk about the bounded sequences. So a number C is a lower bound for the sequences an if C is less than or equal to an holds for every positive integer n. And similarly, D is an upper bound if an is less than or equal to D. So if the sequence an has a lower bound, it is said to be bounded from below. And if it has an upper bound, it is said to be bounded from above. So a sequence is said to be bounded if it is bounded from above and below. So then you can read what else is going on here. So furthermore, a sequence an is bounded if and only if there exists a positive constant m such that the absolute value of an is less than or equal to m, holds for all positive integers. And this is the important part. If a sequence converges, it must be bounded, but a bounded sequence need not converge. And then the other thing here is that every increasing sequence that bounded from above is convergent, but then every decreasing sequence that bounded from below is convergent. So the limit of a convergent increasing sequence is an upper bound for the sequence, and similarly, the limit of a convergent decreasing sequence is a lower bound for the sequence. So let's look at the first one here. So it's 1 over n. So if I write out the terms, I have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. So I see that these are actually just decreasing. All right, so these are monotonically decreasing. And I see that my upper bound is 1, and then the values go down from there. But if I want to find the lower bound, then I would need to find the limit as n goes to infinity of 1 over n, and I know that's 0. So the lower bound is 0, and so this converges to 0. All right, so as I get these unit fractions here, 1/5, 1/6, 1/7, they're not going to ever go negative because n was greater than or equal to 1, but at the same time, though, we have to see that there is still a lower bound, and it will get close to 0, but never be equal to 0. So, do you have any questions, Maxwell?
That's all right.
Okay, yeah. This isn't, in my opinion, I don't think that this is too difficult, but here's another one. So if I look at n squared over n plus 1, then I'll write out the terms. All right, so if n is, say, 1, I get a half. N is 2, I get 4/3. N is 3, 9/4. N is 4, 16/5, and n is 5, 25/6. So I see then that this does definitely seem to be increasing. So this is monotonically increasing, and you can check if you would like, but I can guarantee you that this one actually is. All right, so I'll show you just so that you don't feel like I'm scamming you here, because you never know, like it. So I need to show, if I want monotonically increasing, that the a n is less than or equal to the a n plus 1. So this would be the, whoops, here it is. Uh, limit as n goes to infinity of n plus 1 squared over n plus 1 plus 1. So I need to use L'Hopital's rule here, because I have infinity over infinity and infinity over infinity. So I have limit as n goes to infinity of 2n over 1, and then limit as n goes to infinity of, that will be, what is it? What is, oh yeah. So 2n plus 1 all over n plus 2. So then I can, like, just go ahead and figure out here that this actually is, all right, still infinity over infinity. So then that will be, well, if I find that derivative, 2 over 1. So I I I actually know here then that well, in this particular case, if you see what is going on here, right? That, well, 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 if you see what's going on here, then actually, you know what? This actually should have been, 1. So I don't know why. I was trying to figure out why I said that, but I was looking at something weird, and I don't know why I said that, because I'm looking at something weirdly, and I'm not sure what I was looking at weirdly when I decided just to not actually go ahead and just simplify this n plus 2 here. But there we go. So now, I actually think that did not look like a plus to me, but there we go. So now we actually see that we have 2n and 2n plus 1 here. So this will be 2n, and that's 2n plus 2. And if I add 2 to the 2n, I'm always going to get a number that's bigger than this number. So I know that this is always bigger than this. So it's definitely always monotonically increasing. But then I know that the limit as n goes to infinity of 2n is infinity, and the limit as n goes to infinity of 2n plus 2 is also infinity. So I know that the upper bound is in infinity. So that means upper bound infinity. That means that there is no upper bound. But then that means that the lower bound then is going to just be the number that we started at again. So that would be 1/2. And then that means since there is no upper bound here, that this actually goes ahead and it diverges. All right, so these numbers as n goes to infinity will go to infinity, so that means it's not going to converge to a finite value. So now, do you have any questions about that, Maxwell? No. All right, so now we have -1 to the n. So if n is, say, 1, then we get -1. If n is 2, we get 1, n is 3, we get -1, n is 4, we get 1 again, n is 5, we get -1, n is 6, we get 1. And so what we see here is that this is one that is not monotonically increasing or decreasing. So this is non-monotonic, monotonic. So non-monotonic because the terms are alternating. So the terms are alternating here. But then I see though that the lower bound is actually -1, and the upper bound is actually 1, but this still diverges. So this is a situation where we have so an has an upper and lower bound, but still diverges. All right, so now the next page really is just, well, actually, not even the next page. This part here is just for you to get some examples of practicing, like writing the nth term. So I actually gave you what the answers are already here. And this is just so that if you want more practice of how to get the nth terms, that you could try to figure out how you would figure out the pattern so that this is what you would get for all of these. But other than that, that is the end of this section here.